Tonight's distinguished speaker is Professor Brad Marston from Brown University. Professor Marston graduated from California Institute of Technology. Then he went to Princeton University to pursue his graduate studies in physics, where I happened to meet him. And he received his PhD in 1989. He has held research appointments at Cornell University, University of California, Santa Barbara, MIT, and École Normale Supérieure in Lyon, France. So Brad joined the faculty of Brown in 1992, and he's built a distinguished career in both research and in teaching. He is an Alfred Sloan Foundation Fellow. He's a Fellow of the American Physical Society. He currently serves on the board of directors of the American Physical Society. And in 2008, he was the National Science Foundation American Competitiveness Award winner, quote, for his transformational interdisciplinary research harnessing methods of theoretical condensed matter physics to attack climate modeling, and also for his exceptional contributions to the advancement of the education, contributions to education and mentoring of students. So Brad is also a connoisseur of the outdoors, nature, and you can learn about his interests at Brad Marston. So without further ado, it's my great pleasure to give the floor to Brad.
Thank you very much, Jim. It's a delight to be introduced by my former professor who taught me condensed matter physics when I was a graduate student, and I still have very fond memories of your course. Tonight's lecture brings together a topic of obvious interest to the Aspen Center for Physics, quantum physics. Many of the physicists here work on quantum physics, and climate change, which may seem like something of a surprising connection. But I hope that the connection will become clearer as tonight's talk goes on. Now, I should say that as a resident of the smallest state of Rhode Island, I have another connection to climate change, which is that the state of Rhode Island is frequently used as a unit of measurement for the climate system. For example, when ice is breaking off of Antarctica, frequently the unit of area is the Rhode Island. However, in recent years, we've had to upgrade our system of units to Delaware's because the ice is a bit larger. So even though Rhode Island is the smallest state, it happens to have the longest state name. Does anyone know what the official name of Rhode Island is?
Commonwealth? No, it's plantations. Right?
That's right. It's the state of Rhode Island and the Providence Plantations. Yeah. Because Rhode Island's actually only this little piece. That's what we call Aquidneck Island. And everything else is the Providence Plantations. So we can claim to be the largest in something. Okay, so I want to interweave tonight's talk with something else I've been doing of late, which is section hiking the Pacific Crest Trail. So the Pacific Crest Trail starts in Mexico, right at the border of Campo, and extends up through California, where California is actually more than 50% of its length. It goes through the Mojave Desert, and then along the Sierra Nevada, and then up through the Klamath Mountains, and then along the Cascades for the rest of its route until it gets to Canada. And I began hiking this in 2013. I wouldn't be able to get 5 months off from my dean to do the whole thing all at once. So I have to do it in bits and pieces, a couple hundred miles each year. But this has been an extraordinary experience for me, seeing firsthand some of the changes that are occurring to our natural world, some that may be related to climate change. I like this view in particular of where the trail goes from near the Salton Sea along the Sierra Nevada. I've now completed the Sierras, and I'm working on different segments. We'll see a couple pictures from the rest of the trail later on. In fact, actually, we'll start right now. Yep. So this is a glacier in Yosemite National Park, and the trail goes right by this glacier. It's also, at that point, the same as the John Muir Trail. This is a picture of the Lyell Glacier from 1883. And we'll see that this plays an important role in the talk because this is the glacier that John Muir established that glaciation was an important process in shaping the Sierra Nevada, in fact, mountains throughout the West. So this is a picture of it in 1883, and this is what it looked like when I went by it in 2013. Here's the two together. I'm at a slightly different vantage point, but it's basically the same here. And you can see actually now that glacier is no longer a glacier. It's basically just a snowfield. It's no longer flowing coherently. And so whether or not this is due to climate change is an important question. It seems pretty clear that climate change is involved in the shrinking of the glacier, but there may be some other things going on, which I may have time to talk about briefly. So John Muir is going to be kind of a theme for this talk because I really like this saying of his that probably many of you have heard before. When we try to pick out anything by itself, we find it hitched to everything else in the universe. And that's certainly a common theme here at the center. We're often talking to each other, physicists that thought that they had no particular connection with their different areas of physics find surprising connections. And I'll tell you about one surprising connection, a discovery that I and two young collaborators made just recently connected to climate change. So I want to get into the basic physics of climate because an understanding of that will provide the basis for understanding why scientists are so concerned about the climate and how it might be changing. So we begin by looking at the planet Earth from space. And we think about the sunlight hitting the planet that is ultimately mostly absorbed by the planet, warming it. About 30% of that sunlight is reflected directly back out into space. That's why the planet is visible from space. And we can see especially the clouds and the ice are particularly reflective, but also the oceans and the land reflect some of that light. So the rest of those 6 units of light coming in is absorbed and heats up the Earth and then is emitted back out into space as infrared radiation. So the Earth has the same amount of power coming in from the sun as going out to a pretty good approximation. So by balancing the power going in and going out, we should be able to figure out the temperature of the Earth. But it turns out that if we try to do that, we're using classical physics, we immediately fall flat on our face. In fact, this was the historical origin of quantum mechanics, is to try to understand the radiation from warm bodies. So we're going to have to take a detour into some quantum mechanics to understand how to make the simplest possible calculation of the Earth's temperature. Here's a view of that source of radiation, the sun, but of course blocked by the moon from the recent eclipse last month, which I was lucky enough to see in Wyoming. And you can see the corona streaming out. And when this eclipse occurred, when the total eclipse occurred, we were standing in the middle of a field in Wyoming, south of Casper, and it got quite a bit cooler, very, very noticeable. So it's obvious that the sun is providing direct input to the heating of the local environment. So Richard Feynman offers a very nice way to think about the light that's coming from the sun or light in general. And since I had him as a professor at Caltech, I always like to bring up his lectures in physics. And I can hear his voice, in fact, as I'm telling you about this, because this is one of his favorite things to discuss. So he begins by noticing that particles like marbles or baseballs come in lumps. You have one baseball or two baseballs. And so if we do an experiment in which we have some source of particles, maybe a machine gun or just a batting machine sending off baseballs, and we have a wall that has two holes in it, then the baseballs can go through either one hole or through the other hole, and then they'll end up at the backstop. And if we close hole number 2, the baseballs will only go through hole number 1, and we'll find that the baseballs, if we say send 100 through, will be over here basically, because they're mainly going this direction, and there'll be more of them in this region and less out here. Right? They'll bounce off the walls, but the ones that go straight on through will get a lot right here. And if we close hole number 1 and open hole number 2, then we'll get a bunch over on this side. And if we keep both holes open, then we'll just get the sum of this. The baseballs can go through either 1 or 2, so it'll just add up. Right? Pretty intuitive. But in contrast to this, we have waves, like water waves. And if we repeat this experiment with a source of waves, the waves will impinge on these two holes, and when it goes through, say, hole number 1, we'll get another little baby wave radiating outward. And I'll show you a movie of this with some water waves in just a moment. And out of hole number 2, we'll get these waves. If we close hole number 2, the intensity of the waves along this absorber, where the waves are strongest, where the water is going up and down the most, will be biggest over here. If we close hole number 1, it'll be biggest over here. But if we leave them both open, we get a surprise. We get this rich pattern called an interference pattern. And the interference pattern happens because at certain points, the crests of waves that went through hole number 2 meet the troughs of waves through hole number 1, and they cancel out. We call that destructive interference. And so at those points, the intensity is going to be low. So let's see a movie of that. So here's some water waves. We're looking down on a tank of water. And down here, a piece of wood is going up and down, producing some waves. And it's hitting a screen that has 2 holes here. And you can see the pattern going out. Let's turn this on. And you can see, so here they're adding together. It'll be a little bit slower in just a moment. And here, the waves are canceling out. And then they're adding here together. Right? So this is all classical physics. Newton understood this. Other classical physicists understood this. There's no particular problem, because we either have particles or we have waves. But you can probably sense that I'm setting you up for something. So let's do this with light. So at Brown, we have a very sensitive camera that can detect individual particles of light called photons. And we love to do this demonstration for our undergraduates when we're teaching them quantum mechanics. Because what we're going to do is we're going to shine light through a screen. And that screen has 2 holes. And so if light is a wave, it's going to show an interference pattern. And here's a snapshot of it. We have some bright lines, and we have some dark regions in between. So let me turn this on. And you can see it's scintillating because we're seeing particles that are making up the light. And so we're simultaneously seeing both the wave-like property of the light and the particle-like part of the light. But now we're going to try to trick things. We're going to turn down the intensity of that light until it's just barely sprinkling in. You can't see that interference pattern anymore, right? The light is just dribbling in, particle by particle. It looks a lot like the baseballs now. It's just random. They're bouncing through. And now, what happens when we take a time exposure of that picture? So the computer that's recording the position can record the positions of all these particles. And I'll speed this up a little bit. And there our interference pattern returns. So we simultaneously see that light has both a particle nature and a wave-like nature. And here's where I can hear Feynman saying that Is it a particle, wave, both, neither? It's like nothing you have ever seen before, because nothing in our ordinary experience prepares us for this. And this is a lesson that we learn in physics over and over again. When we look at very small things or very large things, we're surprised. There's some deep difference between our common sense interpretation of how reality is and what we really see if we use some instruments to go a little bit beyond the power of the human being. It turns out the human eye is almost capable of seeing individual photons. So our eye isn't very far from being able to do this experiment without augmentation. So there's an equation that tells us, that relates this. It's due to Einstein, but it's not E equals mc squared. It's actually a much more profound and important equation than E equals mc squared. And it's the one that everyone should really learn about Einstein. It says that energy, E, that means the particles come in lumps. Each photon has energy. That's the energy that's going to heat the planet, is equal to the frequency of the waves. Here's the wave-like nature of light. Here's the particle-like nature of light. And there's a constant in here due to Max Planck, Planck's constant that relates these two things. When Max Planck found this constant, he had stumbled on a new world, the quantum world of physics. But it wasn't until Einstein in 1905 realized that there was a simple interpretation of Planck's constant through this equation that relates the particle nature on one side to the wave-like nature at the other. It captures simultaneously these two properties of light. So what does this have to do with global warming? Let's go back to our calculation of the Earth's temperature. So we have solar radiation coming in from the sun, a little bit over 1,000 watts per meter squared. This is a picture of my new house. One of the first things we did is we put some solar panels on that house to intercept some of this power. This is the second time I've put solar panels on a house. And my wife, who's back in Providence, threw the switch while I was here at the center. And our meter outside, which was set to 0, started going backwards because we're putting power back into the grid. And we're continuing to put power back in the grid. We built this a little bit larger than we need right now because we're anticipating getting rid of our cars and buying an electric car. And it should be big enough to power our electric car plus our house. So anyway, those solar panels convert some fraction of this solar radiation into electricity. But we can use this solar radiation, this power, to figure out the temperature of the Earth. So this is how we're going to do it. We're going to use the fact that a glowing body gives off a certain amount of heat to space. It's proportional to the temperature to the 4th power. And this constant here involves Planck's constant. I'm not going to write it out for you. It's a complicated formula. But that's where Planck's constant lurks. And we're going to relate the heat going out of the Earth to the solar radiation coming in. So S was 1,360 watts per meter squared. A was the 30%, the light that's reflected off the Earth. So we only have 70% that's absorbed. And then this factor of 1/4, that's because the surface of the Earth is not fully illuminated by the sun at any one time. Half of the Earth is in darkness, the night, and the other half is in the daytime. And also, the sun is rather feeble if you're at the poles, and it's strong if you're at lower latitudes. So this factor of 1/4 is just the ratio of the area of a sphere to the area of a disk, the disk of the Earth intercepting the sunlight. We put in the numbers, and out comes the temperature of the Earth. Minus 18 degrees Celsius, 0 degrees Fahrenheit. Well, at least it's an easy number to remember, 0 degrees Fahrenheit. It doesn't look like a very good estimate, but if you're an astronomer, we did pretty well, because this is 255 degrees Celsius above absolute 0. And the actual temperature of the Earth is more like 286 or something degrees Kelvin. So we're not that far off if we measure from absolute 0. But from a practical point of view, 0 degrees Fahrenheit seems like a pretty lousy estimate. Nevertheless, we did OK with our first estimate. And now it behooves us to figure out how to fix things up. Well, it turns out we can fix things up, and in doing so, we'll learn about climate change, and we'll learn about the threat posed by global warming. First, before we do that, let's look at some of the neighboring planets. Let's see how well this formula performs for Venus and Mars. So these are the so-called terrestrial planets, the ones that are rocky and near Earth. So well, I have a little table here. Here's going to be our calculated temperature, the actual temperature, and we'll call the difference between those two temperatures the greenhouse warming. So here's our calculation for Earth. We found out the temperature was about 0 by our calculation, but really the temperature of the Earth on average is about 59 degrees. It's warmer in the tropics, colder in the poles, but on average it's around that. So the difference between our two numbers is about 60 degrees. If we look at Mars, however, the calculated temperature is about -69 Fahrenheit. The actual temperature is about -63. So there's only a 6-degree Fahrenheit difference. And that's because Mars has a very thin atmosphere. It's only about 1/100th the thickness of the Earth's atmosphere. If we look at Venus, its calculated temperature is lower than that of Earth, even though it's closer to the sun than Earth. And that's because it's completely covered with clouds. It reflects 75% of the light off of it. That's why if you look at it right now in the morning, it's a very bright planet. Its actual temperature on the surface is about 800 degrees. So there's a huge discrepancy. And Venus is the opposite extreme of Mars. Its atmosphere is about 100 times thicker than the Earth's. And it's mainly composed of carbon dioxide. And we know that carbon dioxide is a very strong greenhouse gas. So Venus is the poster child for the greenhouse effect, for the power of an atmosphere to control the temperature of a planet. So on Earth, water vapor is the most important greenhouse gas. And so here's a water molecule. And the thing about water is that an infrared photon, the heat coming off from the surface of the Earth, can be absorbed by the water and then re-emitted back down to the Earth. That's why if you are living in a humid climate like Rhode Island in the summer, then at nighttime it doesn't cool off very much compared to, say, Aspen, which has much less water vapor, so the nights cool off more quickly. The infrared radiation can escape more easily out into space. Carbon dioxide also plays an important role in absorbing and emitting infrared radiation. It's about a quarter as effective as water. And the main ingredients of the atmosphere, oxygen and nitrogen, are relatively inert. They don't do much to the absorption and emission of radiation because they're not polar molecules. They don't have charge on them like these more complicated molecules. So here's a view of Earth from space in the infrared band, taken in October 2007. You can see the beautiful circulation of the atmosphere. In the mid-latitudes, we have winds blowing from west to east, and in the low latitudes, we have the trade winds going from east to west, and this kind of pulsing you're seeing is from storms building up during the day in the tropics and then dying back. But the thing I want you to notice is that you can't see the continents in this view. This is looking at infrared radiation, and the atmosphere is completely obscuring the continents underneath because the heat that's being emitted from the surfaces below the oceans and the continents is being absorbed by the atmosphere, and therefore we can't see exactly what's going on underneath. It's very opaque. So we see that the atmosphere is playing a strong role. So here's the astronomical observatories on the top of the Big Island in Hawaii. And the reason that these observatories are way up here is to get above the atmosphere, especially this one. This one observes infrared radiation from space. And it's above the water vapor here, so the photons from different sources in the galaxy or other galaxies can travel unimpeded through the atmosphere to this point. And you can see the clouds down here, down below. That's where most of the moisture is. Here's another island over here. So we can now put all of these ingredients together to correct our temperature formula for the Earth, because we're going to use the fact that as you climb up a mountain, and I'm sure many of you have experienced this here, the air gets cooler. And it gets cooler by about 12 degrees Fahrenheit per kilometer. If we go up a kilometer, on average, the temperature is about 12 degrees Fahrenheit cooler. If you go up 5 kilometers, there is no longer enough water vapor in the atmosphere to send those infrared photons back out into space. So at 5 kilometers up, it's as if there's no atmosphere. And it's at that point that our first calculation applies. So we calculated 0 degrees, and then if we multiply 5 kilometers by 12 degrees Fahrenheit per kilometer, that's 60, 12 times 5, we get 60 Fahrenheit. That's the temperature of the Earth. That's the average temperature of the Earth. That's the basic physics, combining the quantum physics with the fact that the air gets cooler as we go up. And eventually, at 5 kilometers, those infrared photons that were struggling to get out to space are now free and they can travel out. Now, Feynman has had a nice remark about theories. This is a theory of the Earth's temperature. And the remark that Feynman made was that you should never use the data that you use to construct the theory here to say that it confirms the theory. You need something else. You need to try it again on new data. But we have such an experiment that we can perform, and I'm pretty sure most of you have done this experiment. If you're traveling internationally, flying to, say, Europe or Asia, and you ever look at the flight path and the data in front of you on your screen, in your seat, you can see the temperature outside. And I don't know if you've noticed this, but it's almost always the same temperature. It's almost always about minus 60 degrees Celsius. Minus 60 degrees Celsius. It's pretty cold. Can this formula give us that temperature? So the plane is traveling much higher than 5 kilometers. It's maybe, let's see, 10 kilometers or so up, maybe even higher than that, a bit higher than that, 13 kilometers. Can our formula tell us what the temperature will be up there? Well, up there, there's definitely very little water vapor. So the atmosphere is what we say optically thin. It is heated only from below, not from above, because there's infrared photons coming from below, and the carbon dioxide that's still up there in the atmosphere can absorb those infrared photons. But then it can radiate either back down to Earth or back out into space. It can absorb one way, but it can radiate 2 different ways. And that's why it's colder. And in fact, we can calculate how much colder it is. We take that temperature that we found from our simple calculation, and we take the fourth root of 2. That fourth root comes because we had that temperature to the 4th power in our original calculation. We plug that in, and we get minus 60 Celsius or minus 76 Fahrenheit. That's the temperature that you'll see from your plane when it's traveling through the stratosphere and there's no water vapor. So this formula works. We can claim that this simple model for the Earth's temperature gives us a basic understanding of the Earth's temperature. It now allows us to make another prediction. As you all know, the carbon dioxide content of the atmosphere has been increasing. And a few years ago, we passed about 400 parts per million. So back 100 years ago, it was around 270 parts per million. And due to the burning of fossil fuels, mainly also some deforestation, it's been going up steadily since. And here you can see the seasonal cycle. The carbon dioxide concentration in the atmosphere varies over the seasons because in the spring, most of the plants are in the northern hemisphere. They absorb some of the carbon dioxide. And now, at this time of year, the aspen leaves are beginning to fall to the ground, and they're decaying and releasing their carbon dioxide, and the amount goes up. But the overall trend is clear. So sometime in the middle of this century, the amount of carbon dioxide in the atmosphere will be twice what it was before people started burning coal and so on wholesale. How much will the temperature go up? Well, when that happens, when that carbon dioxide is doubled, then the height at which those infrared photons finally can go out into space increases a little bit because there's all that extra carbon dioxide in the atmosphere. They struggle a little bit more to get out into space. And it turns out to be about 150 meters higher. If we plug 150 meters or 0.15 kilometers into our formula, we get a temperature increase of about 1.8 degrees Fahrenheit or 1 degree Celsius. If it were only 1 degree Celsius, we wouldn't be very worried. It's actually going to be more like 2 to 3 degrees Celsius. And the reason for that is that as the Earth warms, more water vapor will go into the atmosphere. That's the main thing that will happen because as water warms, it evaporates. And that water, as we saw, is a very strong greenhouse gas. So that will amplify this number to this kind of range. So now we have some understanding of the Earth's temperature and also how it might be changing as we move further into this century. I want to show you a plot that comes from a more sophisticated model of the Earth's temperature. This is a reconstruction of the temperature of the Earth in the northern hemisphere from 1000 to the year 2000, taken from all sorts of different sources. In the more past 100 years or a little bit more, there have been enough thermometers to directly measure it. But before that, there's more uncertainty because it's coming from tree rings and ice cores and various other sources that have been compiled together. But mostly, the climate has been fairly constant. It's maybe dropped a little bit in what's called the Little Ice Age. Doesn't show up very clearly here. And then maybe it's going up a bit. So what does the prediction of a more sophisticated model show? This is the kind of temperature range that we're going into. You can see that it's going to be deviating quite markedly from the historic past since the Middle Ages. Now this was a simulation. This is a set of simulations that were done almost over 15 years ago. It's from a report of the Intergovernmental Panel on Climate Change from quite a long time ago. Why am I not showing you the most recent ones? Well, the answer is that this plot would be almost the same. In fact, we've known about this result since the 1970s, since something called the Charney Report. If you look at the Charney Report, it basically gets everything right, according to our present understanding. Very little has changed. And the reason it hasn't changed is because it's very robust. It depends on simple physics, the physics that you just saw, these simple equations. It's not because of some fancy computer model. It's because there's some very simple physics underlying this overall temperature of the Earth, what's controlling the temperature of the Earth. However, that isn't really what we want to know. We want to know, as human beings, whether there's going to be more droughts in the West, more hurricanes or stronger hurricanes, and so on. This isn't going to tell us that. This tells us something about the overall planet, but it doesn't tell us about the things that will really affect us or really affect life on Earth. So that's why there's so much activity trying to understand the climate system. Here's an actual instrumental observational record of temperature since 1880, compiled by NASA in this case. The red dots are for the northern hemisphere, and the blue are for the southern hemisphere. And you can see that there's definitely been an upward trend since around the middle of the 20th century. You can see that the northern hemisphere has been warming faster than the southern hemisphere. Part of the reason for that is the southern hemisphere has more oceans, and it takes longer to heat up the oceans. The oceans can absorb heat. This is what was many people talked about a climate pause when the warming didn't seem to do too much, but then in recent years it's been shooting up very dramatically. And we can see that actually from taking the long perspective, there isn't anything particularly special about this. There have been all sorts of variations in the temperature. So I mentioned that what we really want to know is questions about, say, drought in the West. How is that going to change? This is really getting to the heart of the science of climate change. There's so much nonsense that we hear about climate change in the political sphere, and the basic facts of this warming, as I've tried to argue, are very clear. And rarely do we hear about the real science, the science that's going on at this moment in vigorous discussions between climate scientists, including scientists that are here at the center, the really interesting questions. And I want to tell you about a couple of those. So the Earth is warmed more strongly at the low latitudes because the sunlight hits it more directly down here and less up here. And that causes a rich pattern of the atmosphere to flow. We have the trade winds, as we saw, and we have storm systems. All of these things are happening, and it's a rich and very beautiful system. One thing that's been happening in the past few decades is that the amount of sea ice on the Arctic Ocean has decreased dramatically. And in particularly, in 2012, we can see how much that sea ice decreased at its minimum extent, which occurs around now in September. And in fact, it was so much reduced, then ships could go through the so-called Northwest Passage. So a question has arisen: has this reduction in sea ice affected the circulation of the atmosphere or changed some of the things that we are experiencing in the climate system? So a hypothesis has been made by Jennifer Francis that as the sea ice melts, then the temperature difference between the equator and the pole is reduced because the Arctic is getting warmer. It's certainly getting warmer faster than the equator. That reduces the temperature difference, and it's temperature differences that drive the atmospheric motion. So it stands to reason that perhaps that will affect the jet stream that's waving around. So that's an interesting hypothesis. And Jennifer Francis has discussed this, and her collaborators have discussed this in a number of scientific meetings. It's looking now that it's probably fairly unlikely that this is exactly what's happening, yet it's an example of a testable and interesting climate physics question that we can try to answer and that might have some influence on the climate system. So I want to invite you to do your own test of this hypothesis. So for those of you who own a Macintosh computer, you can download for free my app called GCM for General Circulation Model, and you can run it, and you can do your own experiments to test in a very simplified model the Francis hypothesis. Actually, to be truthful, the model is too simple really for this purpose, but it's still fun to play with. In fact, I'm going to do it for you right now. So we launch the model and put on our glasses because we're getting older. And so you can choose a model from up here. You can choose something, the primitive equations, and that's the model we're going to choose. And we're going to choose this Earth-like model. And what I'm going to do is I'm going to spin it up. First, I'm going to make a grid that represents the sphere of the Earth. And it's going to start off with nothing. There's no winds right now. But I'm going to turn on the solar radiation. I'm going to start warming the equator relative to the poles. And we're going to start seeing that the atmosphere stirs. the thing we're showing right now is a quantity that's been the subject of this of the workshop I'm involved with here at the center called vorticity. But let's look at the east-west winds, and we'll adjust the levels so that we can see a little bit more clearly what's going on. So we have some winds developing. It's not this planet is. It's not there yet. It's kind of evolving right now to try. The atmosphere has to get into circulation. But this red up here means that the winds up at these latitudes is already blowing from west to east, like it was in that satellite view we saw. And down here, it's blowing from east to west. Those are the trade winds. And now you can start to see a little bit of modeling occurring. And this is the beginnings of storm systems that are beginning to develop in this simplified model. And we're going to take a look now at, we're going to try to highlight that by looking at something called the kinetic energy. And let's take a view of the North Pole, since we were kind of focusing on that North Pole in the polar ice experiment, the fact that the sea ice was decreasing. And we can see that now we're getting some interesting circulation. I'll have to let this run for a little bit longer, probably another 5 minutes before it kind of settles down. So I invite you to do that yourself. I'm just going to go ahead and show you a movie that I made recording that so that we can see a little bit more quickly what's happening. So this is looking down on the North Pole of the Earth in this little model. And this is basically the jet stream. We're seeing it whirling around. And even though this little model is just running on my laptop, we can compare it to actual observations. So this is observations that NASA has produced of the jet stream. Here we're looking down on the North Pole. And let's let this movie run. And we can see that this jet stream changes in character. It meanders. And in fact, for the time period showing from a few years ago, it's going to develop a very strong meander here. And it's got locked here in this position for a while. That's when there was a drought in the west because the storm systems were traveling to the north of the Rocky Mountains. And we had a drought in the past few years. There was a pretty severe drought, which I want to come back to in a moment. So the hypothesis is that perhaps the melting of the Arctic sea ice is affecting the circulation, and perhaps it's trapping, causing a locking of the flow. And it was just such a locking that occurred recently when Hurricane Harvey approached Texas. Normally, the hurricanes would be swept away, but you remember this one got stuck, and that's the reason why Houston received these incredible rainfalls. It's because this blocking of high pressure prevented this from being swept out of the area for several days. So as I say, it's probably not the case that the Francis hypothesis is correct. And if you try to play around with the temperature difference in even my simple model, you find that the circulation doesn't change very much. But this has been a topic of a lot of discussion. And in the Aspen area, there are a couple other scientific institutions that are interested in climate change. And in particular, one that used to be located just down the street, but is now in Basalt, is the Aspen Global Change Institute. And earlier in the summer, they had a workshop, Understanding the Causes and Consequences of Polar Amplification. One of our workshop participants here, Paul Kushner, was participating in this. And there was a lot of debate about how the Arctic is changing and the consequences of those changes. So this is the kind of true scientific arguments, vigorous back and forth that's going on between climate scientists as we try to figure out how the climate system is changing. This is the true scientific arguments that are happening. Now, one thing we shouldn't forget in worrying about climate change is just how beautiful the climate system is. So we've been focusing a lot on the atmosphere, but the ocean is also a spectacular example of a fluid in circulation. And here we see the Gulf Stream, and then all these little whirls, especially coming off of the southern part of Africa. We'll get down there in just a moment. Here we go. Look at all these little whirls. These aren't hurricanes. These are circulations of ocean current. And I mentioned that our workshop here is focused on vorticity. In fact, the title is Vorticity in the Universe. And this is perhaps one of the most beautiful examples of vorticity in the universe. All of these little whirls in the ocean system. So here's our Vorticity in the Universe program that's been occurring here at the Aspen Center for Physics. And we've been surprised to find that vorticity is also a concern of particle physicists at the very smallest scale to cosmologists looking at giant clusters of galaxies and pretty much everything in between. Vorticity, the swirl of fluid, is of interest. So I've told you about quantum mechanics playing an important role in understanding climate. But we made a discovery this past year of in a very unexpected way that quantum mechanics plays a role in understanding the climate system. In fact, while I was hiking along the Pacific Crest Trail last summer, I was out there for a couple weeks and had a lot of time to think, which doesn't happen too much anymore when I'm back at Brown and distracted by things. I had a lot of time to think, and I had this idea that there was a similarity between something that condensed matter physicists like Jim study and something that climate physicists study. And I knew I wasn't smart enough to figure this all out, so I called up two really bright young French physicists to help me out, and we made this discovery, which I want to tell you about. So an important factor in our climate, and especially in the oceans, is the El Nino. And this is an illustration of warm water moving from the Western Pacific to the Eastern Pacific and then back due to an El Nino that just occurred, a particularly strong El Nino. And this motion of warm water, let's see this over again. Let's start this over again here, is transported in this initial stage when this blob of warm water moves towards South America by a wave that's called a Kelvin wave. And it's right on the equator, you can see, at 0 degrees latitude. So this is, it turns out, mathematically identical to a phenomena that physicists have been very interested in for the past few decades, and in fact was recognized in the most recent Nobel Prize in Physics last year. This is the Nobel Prize in Physics for the recognition that the mathematical field of topology plays an important role. And the prize went to Duncan Haldane, Mike Kosterlitz, my colleague at Brown, and David Thallis. And David Thallis, his work was the one that interested me, because what he discovered is that in a magnetic field, or he explained rather, in a magnetic field, electrons go around in these circular orbits, kind of like those vortices that we just saw, except at the edge of our sample of maybe silicon, where they can't go around in a circle because they hit the edge, and so they just bounce, and they bounce only in one direction. They go in one direction. This is a little bit like our Kelvin wave. And in fact, we realized that the mathematics, the topological mathematics of this kind of physics of electrons in a magnetic field was identical to the physics of our Kelvin wave. So I'll show you a little illustration of this. So here's our sphere illustrated with my app, and I've dropped a rock onto this sphere, and it sends out a wave just like a rock would on a pond. But this sphere right now isn't rotating, so that wave just goes out in all directions. If we view it on a longitude-latitude plot, it looks like this. It goes from one side of the sphere to the other, and then it comes back, because it comes to that point, and then it just comes back. And it'll just go back and forth, back and forth. So let's now turn on the rotation of the Earth. The rotation of the Earth is like the magnetic field in that experiment, that quantum Hall effect. There's the Kelvin wave. It's stuck on the equator, and this thing is very robust. It'll just go around and around and around. So we now understand that these two seemingly disparate areas of physics are intimately connected. Now, when I was on the Pacific Crest Trail earlier this summer, since I'd done the Sierra Nevada, I moved up to Oregon after a climate meeting. And I was in the Eagle Creek area, which is a very famous area for Pacific Crest Trail hikers. And I was planning to camp here on July the 4th. And there were a lot of people camped in that campground. And some of them were not very smart and somehow started a forest fire, probably with fireworks. And in fact, I was the one who reported this forest fire. You can see I caught it at an early stage. There was this explosion. We started smelling smoke. I had my satellite communication device, so I was able to communicate with my wife back in Rhode Island, and she called the sheriff. This Indian Creek fire has now, in this canyon, there's now been a second fire started a few days ago by a couple teenagers with some fireworks. And it's become a gigantic fire that has completely engulfed the canyon. And it's so large that it is now spread across the Columbia River to the state of Washington. Now, one of the reasons, besides human stupidity, why this fire happened is that the Northwest has been in the grips of a drought this summer, a pretty severe drought. It hasn't rained for a long time, so it was pretty ripe for ignition. A lot of other things going on. The Forest Service had been suppressing fire for many years, so things had been built up. So everyone had to leave. And in fact, you might have heard that after the second fire occurred, the first one that I had seen was still burning at the upper end of the canyon. Then these teenagers set off the fire at the lower end, and it trapped 150 hikers in between the two fires. And they had to be rescued by the firefighters. But I want to show you why this canyon is so spectacular and also so dangerous. It's the steep canyon cut into the basalt. And this is a famous part of the Pacific Crest Trail that, so as I was leaving, it's called Tunnel Falls. And you can see carved into the basalt back in the CCC era, this trail was made. And you can go right behind the waterfall. And it's really refreshing and very wonderful. That's why so many people were in that canyon. But now it's all burned. So I don't know what's going to happen. It's burned all the way back from the Columbia River to way up. In fact, it's affecting the reservoir for the city of Portland. So you might have noticed some of the smoke from this fire yesterday. Because the atmospheric circulation, those waves that we saw, those meanders, are bringing the smoke from that fire here, plus a whole bunch of other ones in Oregon and Northern California and Washington, and sweeping it down. So I led a group hike up to the Maroon Bells for some of the participants in our workshop yesterday. It was carefully planned for yesterday. And we got up there, we could barely see them because of all that smoke. But fortunately, it's a little bit clearer today. So that brings me to another institution that is interested in climate change, and that's the Rocky Mountain Biological Laboratory. It's a one-day hike from here over to Gothic, Colorado. And a number of us hiked over there a few years ago when we were at the Aspen Center for Physics, and we met this fellow, Dr. John Hart, who's been warming a Rocky Mountain meadow with some lights for the past several decades as a simulation of the effects of climate change on this meadow. And he's been studying the changes that have been occurring to this meadow. And unfortunately, one of the changes is that the flowering plants seem to be reduced, and sagebrush seems to be increasing. So the Rocky Mountain Biological Lab, and that's one of many things that are going on over there, focused on the biosphere, the biological activity of the Earth. Now, the federal government has done a pretty good job up till now funding the basic science of climate science. But there's been a change recently. And I want to show you this because I think it's very important that everyone know what's been going on. This woman has just received a grant from the Department of Energy for some research having to do with the carbon cycle. The Department of Energy funds quite a bit of research in climate change. And she's been told here that before she can get this grant, I have been asked to contact you to update the wording in your proposal abstract to remove words such as global warming or climate change. This is being asked as we have to meet the president's budget language restrictions and don't want to make any changes without your knowledge or consent. Well, at least they asked her. And then they highlight, helpfully, the appearance of climate change, where she's supposed to remove this. And journalists have dug into this and found that there were other grant recipients who have received the same message. At the Environmental Protection Agency, people who have already received grants to study climate-related subjects have been told that their grants have been canceled. A political operative has been reviewing these grants, something that's unprecedented because they're usually decided by panels of scientists, and has canceled the grants, the funding. And at NASA now has a new administrator who is a well-known denier of climate change. We saw some of the NASA's contributions to climate science earlier in the talk. Well, these kinds of things haven't and aren't completely novel. Back in Muir's time, he also dealt with a lot of skepticism about his theory that glaciers played a major role in shaping the Sierra Nevada, and particularly Yosemite. And in fact, he had a major antagonist. His antagonist was a Harvard professor with all the right credentials named Whitney. And this is what Professor Whitney said. He was a professor at Harvard and also chief of the California Geological Survey. Muir is an ignoramus and a mere sheep herder. So, however, Muir was more correct than Whitney. Whitney thought that this was largely caused by faults, earthquake faults. And it turns out there's a little bit of truth to that. There are faults that weaken the granite and that the glaciers then shape. And so today, Mount Whitney is the highest mountain in the continental United States, and Mount Muir is a little satellite peak right off the edge of Mount Whitney. And so I was thinking about all this as I was hiking past it on the John Muir Trail back in 2013. Around the Aspen area, I was surprised. Paul and I climbed up to Mount Sopris last weekend. And I was surprised, maybe many of you know this, but there are beautiful rock glaciers. This is the rock glacier, one of the rock glaciers viewed from the eastern summit of Sopris. Rock glacier is a combination, as its name refers to, rocks that are helping to insulate. You can see some of the snow here, helping to insulate the snow. So the whole thing, though, can still flow like a glacier. It's an echo of the glaciers that once shaped Mount Sopris and the other mountains in the Elk Range. And it left me wondering how much longer this rock glacier will be there. Apparently it's quite famous. There's been a number of studies about these rock glaciers. Well, I'm at the end of my talk, so let me leave you with this picture of John Muir with Teddy Roosevelt standing on the edge of Yosemite Valley. And I'd be happy to try to answer any questions you might have. Thank you.
Over here on the left.
You said there was a pause, and it looked like it was just around 2000 and a little after. Have you been able to understand why that would have occurred?
There's been a lot of work on that, and that's an interesting question. One thing we know is that although the atmospheric air temperatures paused, the amount of heat going into the ocean didn't. And actually, from the point of view of where the heat goes, the ocean is the big gorilla. The atmosphere is like a little thin eggshell. And most of the heat goes into the ocean. So that has just been going up steadily since we've been able to measure that carefully. We had enough measurements. The atmosphere does complicated things. And why that happened, why there was some pause, and we saw pauses, it was certainly irregular over time, is really an important question and something that we don't fully understand. So there's some interesting things going on in the atmosphere.
You didn't mention methane, and some of us are very worried about permafrost.
Yes. Yeah, methane is a strong greenhouse gas too. And in fact, it's stronger than carbon dioxide. And so it's important to control source release of methane from, say, fracking. And also there's the possibility of methane being released from permafrost, as you indicate, as the Arctic heats up. Yeah, so that's an important subject, and I just didn't have time to talk about it.
Is there, are there models that are making predictions now of what the effect will be?
There are people that are trying to estimate the size of the effect, and I haven't followed this carefully. I know that some studies seem to indicate that it shouldn't be the permafrost effect shouldn't be too significant in the near future. But I'm not an expert on this, so I hesitate to say anything conclusive.
One of your early equations that you used to compute the temperature of the Earth seemed to assume a black body distribution to the radiation. Is that reasonably accurate, that assumption?
Well, you can view my correction to the temperature when I accounted for the atmosphere as a correction to the black body. So we basically started with a black body, and we found that gave us an Earth that was too cold. And then we changed the properties by taking into account the atmosphere. So to that, in the infrared, we're basically saying that, no, it isn't quite a black body. We need to correct it this way. And also, we know in the visible light it isn't a black body because literally we can see that it's not black. The planet is visible from space.
Going with your temperature, there's an assumed distribution of the radiation versus frequency that's not black.
That's right, yes. And so a more detailed model would take into account all of that physics, which I've suppressed here. Yeah.
Take the gentleman here.
Yeah, there's been a recent book on computer modeling for climate out of NOAA, and an article in Science Journal in the last 6 months or so, that cloud formation is the most critical problem today in climate models, and they have to use parameters or secret sauce to correct the models to doing that.
Yes, so the largest source of uncertainty in this projection of the temperature of the Earth is due to uncertainty in how the clouds will respond as the Earth warms. Now, some of this uncertainty here is due to the fact that these models, different assumptions have been made about how much carbon dioxide people will add to the atmosphere. And that's based on economics and so on, guesses basically. But then the other uncertainty is largely due to clouds, and especially low clouds like the fog off of San Francisco. Those clouds are, because they're low, they're warm, they emit a lot of radiation out into space, but they're also bright, they reflect a lot of light, so they have a cooling effect. And the question is, will they shrink or expand as the climate changes? And clouds have a lot of structure. If you think about fog rolling into the Bay Area, you see all the swirls and structure, and all that structure is missed by the computer models that strive to describe the whole Earth. So actually, that's part of my research program, is to try to get a better description of those types of clouds using some ideas from statistical physics. And a number of us are meeting in Santa Barbara for 3 months in the spring to deal with just that issue. But it's been a tough problem for many decades, and it's basically the reason why this uncertainty hasn't decreased over time. Yep.
In biological systems, you always get compensatory feedback mechanisms when something gets out of whack. And I was wondering, is there any possible feedback mechanisms that might slow global warming, and so are those put into the simulations?
Yes. So the simulations try to include both positive and negative feedbacks. And right now, it seems the positive feedbacks win. That's why that simple temperature of 1 degree that we estimated then got boosted to 2 to 3 degrees. Yes, so for example, if there are more forest fires, that might increase the reflection of the land underneath because you don't have that dark canopy. And so that could be a kind of cooling effect that would be an add-on or a reduction to drought. But I wouldn't recommend encouraging it. Yes, so there's many things, and the biosphere is probably the most complicated thing to account for all the positive and negative feedbacks. Yep.
It's great to hear about the ways in which you're understanding the science in simple ways that I, a retired physicist, can understand. I appreciate that. But have you ever tackled an even more complicated system? Have you ever tried to sit down with a senator who has an open mind and who in general supports science? We've got one here in Colorado.
Yes.
Corey Gardner. He's a big supporter of science. What would you try to do if you had a chance to sit down with him and he gave you 10 minutes to explain this to him?
That's a very good question. Unfortunately, or fortunately, I don't have much practice doing this in Rhode Island because we have a very smart congressional delegation, and they understand this. I think that actually many senators, even ones with public statements to the contrary, actually understand this, but they can't afford to take that position because it's become a kind of litmus test. So the rational arguments, such as the type I presented here, may not have the kind of effect that we want, and it will require somebody smarter than me to solve that problem. And I'm not a political scientist, so there are a lot of smart people thinking about that, and maybe something new will come along. Yeah.
Sir, I thought this was one of the best slides, and I really enjoyed this. What I don't understand is if you took this back thousands of years, and we're trying to understand the 15 to 20,000 year cycle for glacialization, how does that fit in?
Right, so that's a whole nother story. 20,000 years ago, where I live, the Rhode Island was under a mile of ice, and so a very different climate. And so that's a very interesting question. How do we get that out from a climate model? And there's been a lot of work on that, and it remains a very active area. There's some ingredients that we know are playing a role. We know that the orbit of the Earth changes, and in various ways, and that changes how much sunlight is absorbed at different latitudes. And we also know that back during the Ice Age, there was a lot less carbon dioxide than even during this pre-industrial period. So that reduced the greenhouse warming further. And in fact, you can use the fact that we know roughly how much colder it was during the Ice Age to estimate the climate sensitivity. And we get numbers that are similar to the kind of numbers that are generated by the arguments that I presented. So that's another line of argument that suggests that we're on the right track.
Early on in your presentation, you talked about the actual temperature of the Earth and the calculated temperature of the Earth, and the difference you attributed to climate change.
Well, due to greenhouse gases.
Greenhouse gases.
That would be true even if there weren't climate change.
Oh, well, then maybe that answers my next question, because then you took the same calculation to Venus and Mars, and the difference in that temperature attributed to climate change or greenhouse gases. And if greenhouse gases or climate change is man-made, how could you say in Venus and Mars that
Right.
you had the temperature difference?
So when I was talking about those planets, I was talking about them in their natural state. So the natural state of Earth has water vapor and carbon dioxide in its atmosphere, some methane too. So that leads to this warming above our calculated temperature. Forget about climate change. That's just how the Earth was. In the case of Mars, there's almost no atmosphere. So their simple calculation just applied pretty much straight on. In the case of Venus, nobody's, as far as we know, it was probably by natural processes that Venus has such a thick atmosphere, and we could talk about why that is. But it just has a huge, thick atmosphere of carbon dioxide, and we know that carbon dioxide has this warming effect. So if we apply the same reasoning that I applied to Earth to Venus, we can get Venus's temperature out too. That would be another that's another nice check of that formula. Yeah. So those are just the natural state. And then we can ask, well, now we start altering Earth's atmosphere. How much additional warming will occur? And that's the next part of my argument. Okay. There's a question over there.
Oh, yes. Yeah, if you could go back to your slide that had the drought and then the Texas hurricane
Yes.
in there.
Okay.
Curious to know if you have an opinion on what's going on now, because when I was looking at that hurricane and watching Irma coming up, I'm thinking that they're going to just superstorm in there. We got two other hurricanes in the pipeline, or tropical incidences.
It's September.
Is it possible that everything that's holding that back is just going to turn this into big red and big blue?
Well, this is a snapshot from August 27th, and it's no longer like this right now. In fact, the smoke cleared out of the valley, and the circulation is we're now getting some circulation coming up from the south. This high pressure has actually moved to the west. So, things get stuck for a while, and then they break free and they move. And this particular circumstance that set up this situation with all the precipitation here no longer holds. There are other things going on now. We have these 3 hurricanes in the Atlantic. That's not so unusual at this time of year. September is the peak in our hurricanes, although Hurricane Irma is certainly extremely strong, and it's been aided by unusually warm water temperatures. And the concern is that those warm temperatures extend all the way up to Florida, so that hurricane is probably going to maintain its strength all the way until it hits Florida.
That's the largest storm they've ever seen, right?
Well, by some measures, yeah. There's been storms in the Atlantic that have had lower pressure in the center. But yes, it's certainly extremely dangerous.
If the high pressure set up again, is that potential to be looking for?
No, I don't think so. At least the projections are that hurricane will move through rather quickly and won't stall, as far as I know.
If you're looking at this just through time as hurricanes go, would that influence it? Well, we've got fires. We've got 150 fires going on in the West right now.
Right. So this persistent ridge, there has been a persistent ridge, but it hasn't always extended down as far. So, yeah.
One more question over here.
Right. The oceans are a huge store of carbon dioxide. As they warm, does that change how they store or the rate they store it? And does that affect any of your plots that are projected up? Can you explain that?
Yes. So, in fact, if you go back to the plot, the measured carbon dioxide concentration here, let's see, you might notice that apart from this trend and the seasonal cycle, there are kind of some irregularities there that we can filter out the seasonal cycle and zero in on those. That was actually a problem that I looked at. This is how I first got into this field when I was a graduate student, and my advisor didn't get tenure at Princeton, and I was left to my own devices for a year, I started working with an atmospheric scientist named Michael Oppenheimer, trying to understand these kinds of wiggles here in the carbon dioxide. And we could associate them with the El Nino, largely with the El Nino. And the El Nino, as we know, involves changes in the ocean circulation. So, and the ocean, as you say, has a lot of carbon dioxide, and it also, El Nino affects the Amazon basin, it affects how many fires there are, and so there is some rich dynamics between the carbon dioxide that's stored in the ocean and in the biosphere and in the atmosphere. And they're connected in various ways that we're still trying to understand. Yeah.
One more question here in the front.
Oh, I just kind of was asking for clarification. Wouldn't more CO2 be released as it gets hotter from the ocean because it can store less?
Well, that's one, you might think that, it's like if you have a soda and you warm it up, it goes flat more quickly. But there's something that competes against that, which is that as the surface water gets warmer, it doesn't overturn as much. It's because warm water on top of cold water is stable, we call it stratified, then the CO2-rich waters beneath don't come up to the surface where they can release that carbon dioxide. So it's, as is often the case in climate change. In fact, I had that very idea when I was trying to understand this, and then so an oceanographer set me straight, and he said, well, actually, it's going to go the other way. So we have to be careful for the, that these intuitive ideas might not apply so simply. Yeah, that's a good question. Let me just close by saying, well, we have these three nice scientific institutions in the Aspen area, and climate science is struggling right now. It could use your support, so consider making a donation to one of them. Thank you.